Hello, in this video we're looking at complex numbers in polar form. So this is quite a crucial key video for you, and we're going to cover a real key concept here. So far you've had complex numbers in what we call the rectangular form, and that's where we write it in terms of its real component and its imaginary component, and those are sort of represented in an x and y basis, so like what you used to on a Cartesian plane. So that number's usually coming out of the origin like so, and represented by the point at the end. Now when we're going into polar coordinates, we're using different coordinates to describe that point. And what we're doing is we're using the information that is the length of that number, so that's the modulus r, and the argument, which is the angle. So I've talked about this a little bit already, and so that angle there is the argument of z. Okay, and that's another way to describe a complex number. So it's written over here in some notes as well, and as you'll hopefully recall that the modulus is written like that as well, and you've got the formulas for that on your formula sheet as well. So here's the modulus and here's the argument. So I'm going to explain these things in a bit more depth, and hopefully you'll see that it's actually just a simple definition of how to describe something. So in this first example here, we're transforming from rectangular form to polar form. So this is the number that we're transforming. So before I even get anywhere, I'm just going to draw up an argand diagram so that we can visualize what's going on here. And you'll notice that I've gone quite far in the negative with this one, because in this particular example we're going down to negative 3i, and we're going to positive 2 in the real, and so our complex number is there. And so if we were to draw a vector out to it, it would look like that. Now the modulus is actually the hypotenuse of this right angled triangle that we make, and so if that distance is 2 and that distance is 3, then the modulus, which we can write like this, is going to be equal to the square root of 2 squared plus 3 squared. So that's going to be the square root of 13. Now because we're so happy with surds and stuff, we're not going to evaluate that square root, we'll just leave it as it is. Now the other thing we need to know is the angle from the real axis, and so that's that angle in here. And once again, using trigonometry, this side is adjacent, this side is opposite, so we can say that tan of our modulus is going to equal SOHCAHTOA, so O over A, so 3 over 2. And so using tan inverse, we can work out what that is. Alright, so we'll bring up our calculator, and I'll just check that what mode I'm in. So I'm in degrees, so I need to make sure that I'm happy that my answer's in degrees. And we'll go shift tan 3 over 2, and that gives us 56.3 degrees. So I'll say that theta is 56.2 degrees. I'll just check what that is as a decimal, because sometimes it pops out, in radians, because sometimes it pops out in something that looks familiar. So I'll just check that, and no, that doesn't really look like anything I'm used to, so I'm just going to leave it in degrees for now. It doesn't actually say whether to have it in degrees or not. So when we're putting this in polar form, and I'll just check our formula sheet for this, it wants us to put in terms of cos theta and I sine theta, and that's just related to trigonometry as well. So where are we? Down here. So if we think about our hypotenuse, which is this, and opposite, so to work out the imaginary part, because we're working with opposite and hypotenuse, we would be using sine, so the imaginary part's always in sine, and likewise with cos, we're working with the adjacent and the hypotenuse, and so we'd always be using cosine to find that component. So when we write our complex number, it's going to be our modulus r, so root 13 times cos 56.2 for the real part, plus I sine 56.2 for the imaginary part. And so if you think about it, if you're looking for the real part, you'd just go that times that, and you'd get the real component, which would be 2. And if you're looking for the imaginary component, that times that, and you'd get 3 from your calculator. Now, it gets a bit cumbersome to always write it out like that, so we have a special way of writing out complex numbers in polar form, and we just write root 13 cis 56.2, and that's because the angle is always going to be the same for cosine and sine, and so this is just a shorthand way of saying cos angle plus I sine angle. So that's your cos part, that's your imaginary part, and that's your sine part. Okay, and that will save you a bit of time when you're working. Okay, so that's going from rectangular form into polar form. Let's look at an example where we're going the other way. So here we have a number already in polar form, and they're asking us to put it into rectangular form. So once again, I'm going to draw an Gantt diagram just so that I have a visual idea of what I'm wanting to do here. Okay, so 60 degrees, it's going to be, roughly like this, and that distance there is 2, and that angle there is 60 degrees. So if I'm looking for the imaginary and real parts, that part's going to correspond to imaginary, and that part's going to correspond to the real part. So we'll call this side B, simply because that's going to be our imaginary part, and this side A. And so what we can say is cos theta is going to be equal to A over H, so that's just happens that this side is adjacent as well, but I'm labeling it for our real part. And so we can, because we know that H is 2, rub that out. So because we know that H is 2, we can say that cos theta, which we also know is 60, so cos 60 equals A over 2, and so timesing both sides by 2, that real part A is going to be 2 times cos 60. So we get the calculator out, 2 cos 60, there we go, we get negative 1.9, so A equals negative 1.9, I think we'll go 2 dp, so 90 to 2 dp, and now we'll find B. So for B, because it's opposite, it's going to be sine, so we can say that sine theta will be B over H, and so sine 60 will be B over 2, so B is going to equal 2 sine 60. So we get a calculator out for that one, 2 sine 60, 60, and that gives us negative 0. I've just realised that these are radians, so actually we want to put it into degrees because I'm working in degrees. So I'll just go back and do that last one. So that's 1, so that should be 1, so we won't need to go to dp, and the sine 1 is 1.73. Now you'll get used to recognising these, but I can recognise that that's root 3, and so we can write B as being exactly root 3. Okay, so it's asking us to write in this form here, so we should really write that out in full, and so we can say that Z is equal to 1 plus root 3i. Alright, So obviously there, just watch out on your calculator between degrees and radians, but you'll be fine. But so long as you've got a reasonable handle of your trigonometry, you'll just find intuitively you'll get there. And you'll also notice shortcuts as you go along. Like for example, you don't really need any of this or any of this. I just wanted to go in full so that we see the understanding. You can just jump straight to your cos and sine when you're working that out. Alright, so that's a quick introduction of polar form. It's really useful when we're looking at higher powers of complex numbers, and you'll see that later on. In the meantime, just to make sure you're up to speed, that's the work that you can get on with, and that is where I'll finish this video.